Good morning. I'm Dr. Sudheera, working as an assistant professor in the Department of Pharmaceutical Engineering. Today I would like to discuss about the course Fluid Mechanics and Mechanical Operation. In that, the basic introductory concepts, that is about the fluid and the rheological properties of the fluid. Coming to the rheological properties of the fluid. Before going to that, why we have to discuss the fluid? Because in most of the industries, always we should deal with lots of fluids like water form, some may around like gaseous form or semi-solids. So different forms of fluids we may come across in different industries. So when we are dealing with fluids in any type of industry, we should know better the properties of the fluid, how it is affecting the given temperature and pressure, and lots of different properties like density or viscosity or anything, surface tension, right? So for that reason, the fluid concept is very important before going to the deep into the subject fluid mechanics and its mechanical operations. So coming to the rheological properties, rheology, which is nothing but the branch of physics. We study the way in which the materials deform or flow in response to applied forces. When we are applying the force, how the fluid flow is changing. So study of all these things comes under the rheology. Okay, so the material properties that governs the specific flow in which these deformation or flow behaviors occurs are called as the rheological properties. Before going to that, how many different types of fluids we have in industry point of view? Okay, or in day-to-day life also we can deal with so many different types of fluids, right? So which type of fluid we are using and what is their behavior and what is their properties? So this is the way. We have 5 different types of fluids. They are ideal fluids, real fluids, Newtonian fluids, non-Newtonian fluids, and incompressible fluids. Coming to the one by one, we will discuss in clear. Ideal fluids. These fluids have no viscosity and incompressible, do not lose energy. Before going to that, let me clarify about incompressible and compressible fluids. Whenever we are considering the density changes in the fluid, we refer those fluids are called compressible fluids. Whenever the density changes are not considered, then we call such fluids, we termed it as incompressible fluids. So ideal fluid is one of the fluid which doesn't have any viscosity and it is as incompressible fluids. And second category is about the real fluids. Real fluids possess having some viscosity and exhibit the resistance to flow. So these are the real fluids, what we called as ideal fluids. We generally we doesn't have ideal in nature. We doesn't have anything ideal. It's just a reference fluids. Okay, so all the fluids we can compare with the ideal fluids. That is the reference fluid only. In nature, it doesn't occur generally. Okay, real fluids are when they have some viscosity changes and they exhibit some resistance to flow also, which termed as a real fluid. Coming to the Newtonian and non-Newtonian fluids. So, before going to discuss in detail about Newtonian and non-Newtonian fluids, we have to define what is Newton's law of viscosity. Based on the definitions of the Newton's law of viscosity, we can classify the given fluid is either Newtonian or non-Newtonian. Okay, coming to that. Before that, different properties of the fluids, I just want to mention those are the density, specific weight, viscosity, specific gravity, and vapor pressure and specific volume. These are the general properties of the fluid whenever you have to deal with the fluid in any industry. Let me clarify one thing. Fluid doesn't mean that it is only in liquid form. Okay, whenever we call as a fluid means it is either in form of liquid or in the form of gas. So whatever we had discussed so far will I list out in the tabular form, like type of fluid, density and viscosity. Here I gave some expressions under Newtonian and non-Newtonian fluids. So before going to discuss about this table, let me go to the Newton's law of viscosity first. Newton's law of viscosity. It is nothing but the shear stress between the two adjacent layers of the fluid. Shear stress between the two adjacent layers of the fluid is directly proportional to the value of velocity gradient between the same two different adjacent layers of the fluid. Now, that is nothing but shear stress. That is, you know that shear stress is represented as tau, which is the ratio of force per unit area. Okay, for the given amount of area, how much amount of force you are giving, based on that, how the velocity gradient. So before going to that, so according to the definition of the Newton's law of viscosity, we can write the definition as tau is proportional to velocity gradient du by dy. Coming to the basic term, gradient. What is gradient actually meant? In fluid mechanics or any chemical engineering course, you have to know across the three terms. Those are the rate, gradient and flux. We have to know these three terms. What is rate? Rate is any quantity with respect to time. If you mention the behavior of the any fluid or any substance with respect to time, we call it as a rate. Rate of change of speed we call as velocity. Right? So likewise, anything with respect to time, dt, we call as rate. Similar way, anything with respect to the velocity or whatever the term you can refer that, with respect to distance is called as gradient. Any quantity with respect to some distance, if you mention that, then the term can be represented as a gradient. And third one is the flux. Any quantity with respect to either time, not either, both time and distance or area, sometimes we call as. Both area and time or both length and time. Any quantity with respect to time and length, we call such rate is called the flux. So we should know, as a chemical engineers, we have to know these three basic terms. What is rate, what is gradient, what is flux. Okay, now according to the Newton's law of viscosity, we stated that the shear stress, that is tau, is proportional to the velocity gradient. We already told that gradient is nothing but the distance. Here I am considering the distance because I am mentioning the two adjacent layers. Okay, what is the shear stress applied between the two layers? Okay, so that can be represented in it like y direction. So I am writing it as a dy. How the velocity is changing. So this is nothing but Newton's law of viscosity. Tau proportional to du by dy, where shear stress tau is nothing but force per unit area. Okay, so based on that Newton's law of viscosity, here is the equation. Tau proportional to du by dy. If you observe here, whenever if I take any fluid moving from 0 to x or y direction, some distance of something y, distance y. Okay, so how the velocity will change? If I pour a glass of water on the floor, then observe the flow behavior. At initial point, it has high velocity. By passing through distance to distance, the velocity of the fluid is gradually decreasing. Right? If I write the ratio of velocity to the distance. Generally, we write as a final velocity to the initial velocity by distance. Distance from final distance minus initial distance. This is how we can write difference. So if I apply this equation to our condition, the final velocity will be low or the initial velocity of the fluid is low. Obviously, the initial velocity is maximum because at the entrance of the pipe, the fluid will move with high velocity. Keep on moving to the distance, the velocity is gradually decreasing because of some resistance to the flow. Right. So, if I take this condition, so we will get the negative value. Distance is always positive value. So, finally you get the negative value. So, to compensate the negative value and by removing the proportionality constant, we can rewrite the Newton's law of viscosity as tau is equal to minus mu du by dy, where this negative sign indicating this one. Okay, so that's why we are introducing a negative term in the equation, Newton's law of viscosity, where the proportionality constant mu is called the coefficient of viscosity. Viscosity or coefficient of viscosity we can call, where shear stress is F by A and this is the shear deformation, or we can call it as a velocity gradient. This is how we can define the Newton's law of viscosity. Okay. What are the units of the viscosity? You know, right? Pressure, tau, force per unit area, which is equal to viscosity, velocity by distance, which is equal to force, mass into acceleration, mass m, acceleration, L t power minus 2, divided by area, meter square. Okay, so which is equal to, right? So otherwise we can write in terms of the units only, not in terms of dimensions. Mass into, so kg velocity, kg mass into acceleration. Acceleration is nothing but meter per second square. Kg into meter per second square by area meter square, which is equal to mu into velocity, meter per second by distance m. So finally we will get viscosity mu is equal to kg per meter second. So this is the unit of the viscosity. This is how we can define. Okay, this is how we can write. So here you can see the different units of viscosity, how we can express. We can express in terms of Pascal second or kg per meter second, or sometimes generally we use it to express the viscosity in Newton second per meter square, where Newton is nothing but kg meter per second. Okay, if you apply this here, you can get this Newton second per meter square. This is about the Newton's law of viscosity. So, based on the Newton's law of viscosity, how we can classify the fluids? The fluids are classified into two categories. Those are called Newtonian fluids and non-Newtonian fluids. Coming to Newtonian fluids, what we discussed, the fluids which obeys the Newton's law of viscosity, that is the shear stress is directly proportional to the velocity gradient. If the fluids satisfy that relation, which are those fluids we called as the Newtonian fluids. And those fluids which does not obey that Newton's law of viscosity, then we call such fluids are called non-Newtonian fluids. So the example of the Newtonian fluids are water, air, alcohol, glycerol, etc. And coming to the non-Newtonian fluids, creams, lotions, ointments, suspensions, clay, mud, etc. So many we have non-Newtonian behavior. Okay. This is some of the just I want to give brief description about the differences between the Newtonian fluids and the non-Newtonian fluids. This is the definition where we can have the constant viscosity. Here it is the variable viscosity. Okay, viscosity is constant and variable. Shear stress rate and shear. So these are directly proportional, then we can call as a zero shear rate and zero shear stress. This is how some relation, variable parameters are there. Examples, water and air. Here we can have so many examples under non-Newtonian fluids. Most of the fluids we discussed in day-to-day life, we may deal with the day-to-day life, like syrups we can use, suspensions and ketchups, right? We have like cement floor, okay, sand in water, mud sand, quicksand, whatever. We have so many things we can have in our day-to-day life, we can see. So those are all, most of the cases are related to the non-Newtonian fluids, like paints. Okay, so these are some of the things which I want to mention, the examples under the non-Newtonian fluids. If you observe, these are some of the non-Newtonian behavior. Like I said, ketchups, okay, molten milk, lava, blood is one of the important thing, right? Okay, without blood, no human is there, right? So it is which type of fluid it is? It is under non-Newtonian fluid. So like toothpaste, paints, cream, cornflakes, glues, right? We have so many different types of characteristics of fluids, right? So how they can be representing in non-Newtonian. Coming to the Newtonian fluids, water, right? Without water, no life is exist. So water, milk, gasoline, honey, mineral oil, olive oil, all comes under Newtonian flow of behavior, right? So coming to the deep classification into the Newtonian and non-Newtonian behavior. So if you observe here, whatever the Newton's law of viscosity, if you observe, tau is equal to minus mu du by velocity gradient, du by dy. If you observe this equation, it is in the form of y is equal to m into x, right? Which is a straight line equation passing through origin, right? If you observe here, the blue line, okay, that is, if you draw a graph in between shear stress versus velocity gradient, y versus x, then how the behavior is like. This is y is equal to mx, which is passing through origin and directly proportional. Such fluids we called as the Newtonian fluids. Example, water. Then other classification, those fluids which does not obey this are called non-Newtonian fluids we called. But what are these other lines? Again, in non-Newtonian fluids also we have various number of classifications. Okay, so let's discuss them. In non-Newtonian fluids we have 5 different types. Those are Bingham plastic, pseudoplastic, dilatant, and 2 more classification is also there. That we'll discuss after discussing these 3. If you observe here, Bingham plastic, observe the line. Here it is the line, red color line indicating the Bingham plastic behavior. If you observe this line is also a straight line, but it is not passing through origin, because after applying some initial shear stress, TF, it behaves like a Newtonian fluid. The behavior of such fluids can be expressed in terms of like this. Tau is equal to tau naught minus mu into du by dy. In mathematics, we may heard about the equation called the intercept form of equation. Y is equal to mx plus c, right? So what is that intercept? Here, this is the intercept. After having some external force, the fluid initially have some resistance to move like a Newtonian fluid. After applying such stresses, it again comes into the Newtonian flow of behavior. Such type of fluids we called as a Bingham plastic fluids. Examples, ketchup. Those are also called as viscoelastic fluids. Okay, that is the behavior. Right. And the next classification in the non-Newtonian fluid is the pseudoplastic behavior, which is also called the shear thinning. Shear thinning. What is shear thinning? If you observe the curve, that is the green color curve here, Observe this pattern of the curve. It is also a curve which is passing through the horizon. But if you observe at smaller values of the shear stress, it is behaving like Newtonian fluids. Okay, so this is the pattern at smaller shear rates. Okay, it is behaving. After that, at larger shear stress, it looks like a Newtonian behavior. That is called a shear thinning. So if you observe this curve, it is like some concave downward pattern, right? Concave downward. Okay, so that is also called a shear thinning. Whenever you call as a shear thinning, it is also called as a concave downward behavior, and which is called the pseudoplastic behavior, where the shear stress is directly proportional at lower shears only, and later it behaves like a non-Newtonian fluids. And coming to the reciprocal of the pseudoplastic, like concave upward curve, that is the yellow curve here. Concave upward, this direction. Those type of fluids we call as a dilatant fluid, which is also called the shear thickening fluids. Okay, so examples: water, cornstarch. Coming to the examples of pseudoplastic, paints. Okay, this is how we can classify different types of fluids based on their behavior with shear stress and shear rate. Okay, if you observe all the classifications which we had discussed so far, like Newtonian, under non-Newtonian, like Bingham plastic, pseudoplastic and dilatant, we didn't discuss about anything regarding the time. So all are time independent only. Okay, right? Why time? So some fluids have also classified based on their time dependent fluids. This is the thing. If you observe here, under non-Newtonian fluids, we are classified into time independent and time dependent fluids. In time independent, what we had discussed so far, shear, pseudoplastic, dilatant, Bingham. And coming to the time dependent, we already called. So some fluids are also having the behavior based on their shear stress and shear rate. In addition to that, time also be a factor in their behavior. Those type of fluids are called thixotropic and rheopectic fluids. How we can classify the thixotropic and rheopectic? Whenever shear rate increases with increase in time. When time is increasing, shear rate is also increasing, we call it as a thixotropic. When shear rate decreases with increase in time, like reciprocal, we call it reversible. So those fluids we call it as a rheopectic behavior. Okay, let us discuss brief into that. So these are some of the things we have to mention here. Pseudoplastic, viscosity decreases with increase in shear rate. Examples: ketchup, paint and blood. And coming to the shear thickening fluids, we call it as a dilatant fluids. Examples: cornstarch, wet sand. Coming to the Bingham plastics, so behaves as a solid until a yield stress is applied, like intercept form. Examples: toothpaste and mayonnaise. Coming to the thixotropic fluids, already we discussed. Viscosity decreases over time under constant shear. Okay, over time. Before those what we had mentioned, we didn't discuss anything about the time. Only the time dependent fluids are the thixotropic and rheopectic only. Example: gelatin, yogurt. We all discussed that, right? Rheopectic fluid. Viscosity increases over time. Examples: printer ink, cream, etc. These are another set of fluids called the viscoelastic fluids. Viscoelastic means we already discussed, they exhibit both viscous and elastic fluids. Example: polymer solution. Okay, these are the different types of fluids. This is the classification of fluids. And these are some of the in tabular form which we can remember easily. right? Based on the Newton's law of viscosity. Okay, for Newton's law of viscosity, like Newtonian fluids, which is equal to 0, right? So if it is not equal to 0, we call it as a Bingham plastic, where n is equal to 1. And thixotropic, which is not equal to 0. Like they all are based on the category like Newton's law of viscosity only, which is expressed as tau naught plus minus mu du by dy whole power n, like form, this form. So based on n value, they are classified the different types of fluids. What we have discussed only, based on n here they are discussing, right? When n is not equal to, is equal to 1, then we called as a Bingham plastic, ideal plastic. Pseudoplastic, like less than 1, like lipstick, blood, paper, oils, like thixotropic, printers ink, enamels. And coming to the dilatant, butter, sand, like rheopectic, gypsum plus water. So these are all some of the classification based on the Newtonian fluids. So whenever in examination, in exam point of view, if they ask you about to write the rheological properties of the fluid, you have to mention starting from the Newton's law of viscosity. What is the definition of Newton's law of viscosity? How, based on the Newton's law of viscosity, how the fluids are classified, like Newtonian and non-Newtonian. Under non-Newtonian, again classification. Time dependent, time independent. Under time independent, we have Bingham plastic, dilatant and pseudoplastic. And coming to time dependent flow, rheopectic and thixotropic. This is how you have to write, and the diagram is must, where we have represented a graph in between tau versus du by dy. How the pattern of curves. Okay, that's all for today. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.